In this section, we're going to be talking about solving equations. Now, you might think, well, we've already solved equations, and that's true. We've solved some basic equations. In this section, we're going to solve more complicated equations and equations which require identities to help us solve. So here in example 1, it asked us to solve the following analytically and list the solutions which lie in the interval from 0 to 2 pi, including 0, excluding 2 pi. So we think about the unit circle here, what we're looking for. Whoops. So we're talking about this interval here from 0 to 2 pi. On the good old unit circle, we're looking at angles that are going to start here and then go wrap around up into back to 2 pi. All right, so we don't include the 2 pi because that's coterminal with 0, and so this should capture everything that we want to talk about here. All right. Solving analytically means we want to use our algebra and exact values. Now we will be checking these, or we'll show how to check a few of these on Desmos to see that the decimals tie out. But let's jump into it. Let's look at the first example. Cosine of 2 theta equals negative square root 3 over 2. Now you're fresh off of identities. You might want to jump in and start working identities here. I know some different ways to express cosine 2 theta, and that's one way to proceed here. But anytime you have a trig function equal a number, we can avoid using identities. Okay, let's just cover that up now. Let's just call that thing t. I know how I can solve cosine of t is negative root 3 over 2. That's how I went. That's how we went about solving the basic equations way back in section, what was it, 10.2 and 10.4. So if I want to solve cosine of something is negative square root 3 over 2, the first thing I ask myself is that a legitimate value for cosine? In other words, is it a number between negative 1 and 1? And the answer is yes. So that equation makes sense. The second thing I look at is my quadrants. In which quadrants is the cosine of something negative square root 3 over 2? And the answer is quadrant 2 and quadrant 3. The next thing I ask is, do I know the reference angle? Is this a reference angle I know? And the answer is yes. I know a reference angle whose cosine is square root 3 over 2. That's pi over 6. If I didn't know one, then I can use those inverse functions, the arc functions that we talked about in the last section. Okay, so my reference angle is pi over 6. And so then what we would do is we'd say, okay, well I need a pi over 6 angle in quadrant 2 and a pi over 6 angle in quadrant 3, and I know those from my unit circle. And so I'd say, okay, well, t equals, that would be what? 5 pi's over 6. Then I would catch all the answers by slapping on multiples of 2 pi. Or I would be 7 pi's over 6. Once again, I'd slap on multiples of 2 pi. Slapping on the integer multiples of 2 pi guarantees that I capture all the answers by taking into account all the coterminal angles. Okay, so this is how I would solve this equation. The only difference is instead of a t in there, I've got a 2 theta. All right, so if instead of a t here I have a 2 theta, all that means is I've got 2 theta equal to this, or 2 theta equal to that. So I'd have 2 theta equal to 5 pi over 6 plus 2 pi k, or I'd have 2 theta equals 7 pi over 6 plus 2 pi k. Now how would I solve this equation for theta? I'd have to divide both sides by 2, which is the same as multiplying both sides by a half. So I'd have to take 1/2 times all of this. 1/2 times 5 pi over 6 would give me 5 pi over 12. 1/2 of 2 pi k would give me pi k. 1/2 of 7 pi over 6 would give me 7 pi's over 12. 1/2 of 2 pi k would give me pi k. And once again, pi would be 0, plus or minus 1, plus or minus 2, etc. Right? So this would represent the solutions. Okay, so I solved them. So this is all the solutions. Now I want to figure out which solutions lie specifically in the interval 0 to 2 pi. So in the interval 0 to 2 pi, well, let's see what the first list gives me. I start off, these are, as you can tell, these are pi's over 12. Okay, so sometimes it's helpful, since we're working with pi's over 12, to think about what the interval 0 to 2 pi looks like in pi's over 12. Well, 0 pi over 12 is just 0. 2 pi would be 24 pi's over 12. So I can include angles up to but not including 24 pi's over 12. So let's start here. When k is 0, I got 5 pi over 12 plus 0 pi's. So that's 5 pi over 12. When k is 1, I'd be taking 5 pi over 12 plus pi. Once again, it might help us to remember that pi is 12 pi's over 12. Right? So instead of writing it maybe here as pi k, I can think about this as 12 pi over 12 times k. Right? I'll just do that over here. So pi k would be 12 pi over 12 times k. So if I add, when k is 1, I'd have 5 pi over 12 plus 12 pi over 12. That's 17 pi over 12. And if I let k equal 2, I'd be adding another 12 pi over 12. So that's how I'm getting the rest of these here, is I'm adding 12 pi's over 12. By adding pi, I'm adding 12 pi's over 12. If I added another 12 pi over 12, I'd get to 29 pi over 12, so I've overshot the 24 pi over 12. Okay? Now, let's see if we try the negatives. If I start here and subtract pi and subtract 12 pi over 12, I get into the negative. I'd get negative 7 pi over 12, which is less than 0. So from this family of solutions, I'm getting these two answers. I can do the same thing here. Here I start with 7 pi's over 12. If I add 12 pi's over 12, I'm up to 19 pi's over 12. If I add in another 12 pi over 12, I've overshot the 24 pi over 12. If I started with the negatives, once again, I'd have 7 pi over 12 minus 12 pi over 12. That's a negative, so that would undershoot the 0 here. So these are the solutions that live between 0 and 2 pi. All right. So it's not coincidence that here, this cosine, if I look at cosine t, I get two solutions that live between 0 and 2 pi, because this is like a frequency 1. This is frequency 1. Here, that 2 theta, when we double the frequency, we're going to double the solutions. Hopefully that makes sense. All right, we're going twice as fast. How can I check this on Desmos? So we'll check a couple of these on Desmos. We won't check all of them. But to check them on Desmos, we're going to just, well, I guess we'll default to f of x here, so it doesn't get weird on us. Now we're just looking between 0 and 2 pi. So we'll just graph it there. All right. So that's the cosine piece, and we want it equal to negative square root 3 over 2. Right. So I'm looking graphically where this cosine wave is going to intersect this horizontal line. And sure enough, we see Desmos is displaying 4 solutions. And sometimes it depends. Sometimes solutions will actually give you, Desmos actually give you the pi stuff. Sometimes it won't. And look at that. Oh, it does. It gives us the pi. There's 5 pi over 12, 7 pi over 12, 17 pi over 12. So notice these first two here are pi units apart. So, or the first and the third point here are coming from that first solution family. And then the second and fourth are coming from the second solution family. Okay. If the pi's weren't there, you could just approximate using your decimals. All right. And notice the y values here. These are all Desmos's interpretations of negative square root 3 over 2. Right? So that's how you would check. All right, let's take a look at the cosecant of 1/3 theta minus pi equals root 2. Now, just like when we solved cosecant questions back in, what was it, section 10.4, oftentimes we're more comfortable thinking of sines than cosecant. So I'm going to change this to a sine problem. So the sine of 1/3 theta minus pi would be 1 over root 2. And we can rationalize that to root 2 over 2. And now I just sort of cover this up. And I'm looking for where the sine of something is root 2 over 2. So that's what I'm thinking here. So I'm thinking that in my mind's eye, I'm thinking this is just sine of something equal root 2 over 2. All right, so first off, my first question is does this sine value make sense? In other words, is it between -1 and 1? And the answer is yes. The second thing I think about is my quadrants. Sine is positive, so that's going to give me solutions in quadrant 1 and quadrant 2. All right. So that's going to give me 2 family of solutions. One quadrant 1, one quadrant 2. The third thing I think about is this an angle that I know? Well, sine root 2 over 2, that corresponds to pi over 4, so I do know it. So in quadrant 1, that's just going to be pi over 4 itself, because that's an acute angle. In quadrant 2, that's going to be 3 pi's over 4. So whatever this thing is, the 1/3 theta minus pi is either pi over 4 plus 2 pi k's, or the thing inside 1/3 theta minus pi is 3 pi's over 4 plus 2 pi k's. All right. And now I need to solve this equation for theta. So I would add pi. So I'd be adding pi. So I'd be adding pi to 3 pi over 4 and adding pi to 3 pi over 4. These are the like terms here. There's no k's attached to these pi's, so I'm just going to be adding them to the angles there. So 1/3 theta, pi over 4 plus pi, that's pi over 4 plus 4 pi over 4. That gives me 5 pi's over 4 plus 2 pi k. 3 pi's over 4 plus pi would be 3 pi's over 4 plus 4 pi's over 4. That's 7 pi's over 4 plus 2 pi k. And now for the grand finale, I'd have to multiply both sides by 3. So when I multiply both sides by 3, I'm going to be multiplying not only the 5 pi over 4 by 3, but also the 2 pi over k, and the same thing here. So 5 pi over 4 times 3 would give me 15 pi's over 4 plus 6 pi k's. Seven pi over 4 times 3 would give me 21 pi's over 4. Again, plus 6 pi k's. And k here is an integer, plus or minus 1, plus or minus 2, and so on. So now I try to start listing them out. I want the values that are between 0 and 2 pi. And once again, we seem to be living in pi over 4 world here. So in pi over 4s, that'd be between 0 and 8 pi's over 4. And once again, we're living in pi over 4 world, so 6 pi over 4, that's 24 pi's over 4. All right, so let's check this out. From the first family, if I let k equal 0, I'm already over 8 pi over 4. 15 pi over 4. So if I have any positive values of k, I'm going to be well beyond 6 pi. If I use negative values of k, like a -1, I'd have 15 pi over 4 minus 24 pi over 4. That gets me less than 0. So I actually get no solutions here that live between those numbers. Okay, so that's a bit disappointing. Let's take a look at the second family. If I let k equal 0 here, 21 pi is over 4. I'm already over the 8 pi over 4. If I start looking at the negatives, I'm subtracting off 24 pi over 4. I'm also less than 0 at that point. So I get no solutions here. So even though I have solutions to the equation, right, there are no solutions which lie in the interval 0 to 2 pi. Right? Now, why could that be? Well, let's go back and think about the concept of frequency again. For the regular sine with frequency 1, I would expect two solutions between 0 and 2 pi. The angular frequency here, omega, is a third. So this is running a third as fast as the regular sine wave. So it's slower. It's 3 times slower than the regular sine wave. So it looks like we just don't quite reach it. So let's take a look at this. Let's fire up Desmos here. Let's type in our cosecant. And once again, we'll use x so it doesn't get weird with us. So we'll do 1/3 x minus pi. And we're looking at square root 2. And so by golly, look at that. There's our cosecant graph. It never gets up there. Now, if I lax the restriction here, then we can see we're picking up these values. All right, 15 pi over 4, negative 3 pi over 4. So the equation has infinitely many solutions. It's just got none of them in the interval 0 to pi, 0 to 2 pi. Okay. Now you might wonder, well, you know, what if I change this number? Like if I made this negative square root 2, then we would get a number, in this case 3 pi over 4. So that's just that's one of the professional hazards here of working with these trigonometric functions. We have infinitely many solutions, but none that live from 0 to 2 pi. All right, let's take a look at number 3 here. The cotangent of 3t is 0. Now, when it comes to tangents and cotangents, there's a couple things. One, a lot of times we try to convert this into tangents. The problem is if I try to convert this into tangents, I'd be taking the reciprocal of 0, which is undefined. So I have to remember where the cotangent of 0 is. So cotangent is 0. Remember, on the unit circle, what's cotangent? A cotangent is the x-coordinate over the y-coordinate. So for cotangent to be 0, the x-coordinate has to be 0. That means it's here on the y-axis. That's at our pi over 2 and our 3 pi's over 2. Now you might also remember that the period of cotangent, like the period of tangent, is just pi. So if I'm looking at the cotangent of something being 0, I know that that something is going to be pi over 2, not plus just pi k. Now to solve for t, I would need to divide both sides by 3, which is the same as multiplying by 1/3. If I multiply pi over 2 by 1/3, that's going to get me to a pi over 6. If I multiply pi k divided by 3, that's going to be pi over 3 times k. All right, now it's time to list which of these answers are going to live between 0 and 2 pi. So once again, it looks like if I take the common denominator here, it's pi over 6. So this would be between 0 and 12 pi's over 6. And these pi over 3k's, those are 2 pi's over 6k's. All right, so let's start off with k equals 0. When k equals 0, I just get pi over 6. When k equals 1, I'd be adding 1 pi over 6. So pi over 6 plus pi over 6 would be 2 pi over 6. When k equals 2, I would get another pi over 6, 3 pi over 6. And then I'd get, excuse me, I'm adding 2 pi's over 6. I apologize. Pi over 6 plus 2 pi over 6. So pi over 6 plus 2 pi over 6 would get me to 3 pi over 6. Adding another 2 pi over 6 would get me to 5 pi over 6. Another 2 pi over 6 would get me to 7 pi over 6. And then 9 pi over 6. 11 pi over 6. And then if I went one more of these pi over 3k's, if I add in another 2 pi over 6, I'd have gone beyond the 12 pi over 6 or the 2 pi. If I substitute in negatives for the integers here, I'd be subtracting 2 pi over 6's. If I take pi over 6 minus 2 pi over 6, I'm under 0. So these are our answers. Now we can simplify these, right? So pi over 6, 3 pi's over 6, that's pi over 2. 5 pi over 6, 7 pi over 6, 9 pi over 6, that's 3 pi's over 2, 11 pi over 6. Right. So how many answers did I get? I got 1, 2, 3, 4, 5, 6. Once again, that's not unexpected because the regular cotangent with frequency 1 has 2 answers. This cotangent is moving 3 times as fast, so I do expect 6 solutions. All right. All right, and we can check that on Desmos. This might be the last one I check on Desmos here for a while. Once again, we'll just stick with 3x. And then we're looking at 0 here, the axis. And let's zoom in here. Look at that. Beautiful. 1, 2, 3, 4, 5, and 6. Okay. All right, secant squared of t equals 4. So once again, we've got, first off, we've got a secant squared. I can get rid of that square by taking the square root. So this tells me that the secant of t would either be plus or minus 2. So now I've got 2 equations to solve. Secant of t is negative 2 or secant of t is 2. And you may not be hip to thinking in secants, so we can turn each of these into cosines. Cosine of t is minus a half, or cosine of t is a half. Right? So now I've got these 2 equations to solve. Both of these are legitimate cosine numbers. They're between negative 1 and 1. Here I'm looking for solutions in where cosine is negative, so that'd be in quadrant 2 and quadrant 3. Here I'm looking for solutions. Cosine is positive in quadrant 1 or quadrant 4. Both of these have the same reference angle, pi over 3. And so I know what these answers are going to be, right? I know what these are going to be because it's just cosine t. There's no coefficient there in front of the t. There's no frequency to worry about here. So what are my answers? So t is going to be, all right, well, over here, it's going to be, let's see, I guess if I put them all, since I'm doing plus or minus, since I'm putting them all on here, right? So we can actually take advantage of some of the symmetry here. So we've got the pi over 3 here, and the 2 pi over 3 here. And then I'm picking up also the ones in the opposite quadrants because we're doing the plus or minus 1/2. And so that's pi over 3 plus pi k would get me to here. Plus pi k would get me to there. So I could say, all right, t is pi over 3 plus pi k, or 2 pi over 3 plus pi k, where k is 0, plus or minus 1, plus or minus 2, and so on and so forth. Right? So that would be all of the solutions. And in 0 to 2 pi, Well, I know exactly what those answers are. Pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi's over 3. Right? Those are the pi over 3's that we have between 0 and 2 pi that have a reference angle of pi over 3. And that's it. Okay? So we're getting 4 solutions between 0 and 2 pi, which is not unexpected, because when we take the square root, we get 2 values, a plus and a minus. Each of these is a cosine equation that has a frequency 1, so each of these cosine equations is going to give us 2 answers. 2 answers for the negative cosine, and 2 answers for the positive cosine. All right, let's look at example number 5 here. Let's look at number 5. I got the tangent of x over 2 equals negative 3. The first question is that a good number for tangent? The answer is yes. Remember, the range of tangent and cotangent is all real numbers. So any number you have in there is going to be good. The second is, what quadrants are we working in? Well, if tangent is negative, that means we're either in quadrant 2 or quadrant 4. For tangent to be negative, remember, tangent is the y-coordinate divided by the x-coordinate. That means the x and y must have opposite SIGN signs. So that's going to be in quadrant 2 and quadrant 4. The other thing I know is that these angles are always going to be pi units apart because the period of tangent is pi. All right. Now, is this a common tangent? No, I don't know a reference angle whose tangent is 3. That means I'm going to have to use those arc functions. All right? So that means I'm going to have to use those arc functions. So one way to describe this is, I got the tangent of something is minus 3. That means that something is going to be the arctangent of minus 3, and then plus any multiple of pi k. All right, so that's exactly what the arctangent is designed to do. Now I know from, to simplify this a little bit, I would get x over 2 would be minus arctangent 3 plus pi k, because I can use the odd property of arctangent to move the negative out front. So what this represents would be here, arctangent of positive 3 would be the reference angle. Negative arctangent of 3 would be looking at the angle there that's moving clockwise. Okay. Once again, to solve for x, then I'd have to multiply both sides of the equation by 2. So I'd have to distribute and multiply each term here by 2. So I'd have negative arctangent of 3 plus 2 pi k. And now I have to figure out which of these things is going to live between 0 and 2 pi. So this is where it can get a little dicey. This is where what you might want to do is use decimal approximations to help you. I know that, for example, when k equals 0, I forgot to put what the k's are. You always have to put what the k's are. K's are integers. When k equals 0, I get negative arctangent of 3. Arctangent of 3 is a positive number. So I know when k is 0, I'm less than 0. All right? When I do k equals 1, when k equals 1, I'd have negative 2 arctangent of 3 plus 2 pi. And the question is this between 0 and 2 pi? Well, as I mentioned, arctangent of 3 is some sort of acute angle. It's between 0 and pi over 2. So when I multiply it by 2, it's going to be between 0 and pi. So minus 2 times it is going to be between 0 and 2 pi, but not 2 pi because it's an acute angle. So this will be between 0 and 2 pi. Now if I add another 2 pi to this, then it's going to be beyond 2 pi. All right, so this would be the only solution that lives there. Once again, if you're not comfortable with that, you've got technology to help you approximate these answers. So let's head over to Desmos here. And let's type this in. This was the tangent here. It's x over 2, just like in the problem, and we're looking at -3. Let me zoom out a little bit. I don't know why that's happening here. Boom. There's that 1. So that's the decimal there. Let's take our answer, negative arctangent of 3 plus 2 pi. Let's make sure we're in radian mode too. Excuse me, minus 2 arctangent of 3. And make sure we're in radian mode, which we are. Okay, here we go. And now we can compare the decimals and they track. Okay, so there we go. But the exact answer here would be -2 arctangent 3 plus 2 pi, or I guess you could write that as 2 pi minus 2 arctangent 3. All right? But that's the exact answer, okay? That's the exact answer. If I asked for a decimal representation, I would have said, you know, find a decimal rounded to 4 decimal places. Or if this were an applied problem, you might want to put down a decimal approximation as a courtesy, but that's it. So it's kind of like when you would solve quadratic equations and you would get 2 minus the square root of 3. I mean, that's just the answer, okay? You don't need to approximate the decimal there. That's the exact answer. Only approximate it if it makes sense to do so, all right? So if they ask for it. Speaking of decimals, let's take a look at number 6. I've got the sine of 2x is 0.87. First question, is this a sine value that makes sense? Yes, it's between -1 and 1. Second question is, what quadrants am I dealing with? Well, if the sine is positive, that's either going to give me an angle in quadrant 1 or an angle in quadrant 2. Third question, is this a reference angle I know? No. I don't know an angle off the top of my head whose sine is 0.87. That means I have to use inverse sine, the arc sine. So if I take the arc sine of 0.87, that gives me a quadrant 1 angle. That gives me an angle between 0 and pi over 2, whose sine is 0.87. So our reference angle here is the arc sine of 0.87. So that's going to be the quadrant 1 answer. So 2x is going to be arc sine of 0.87. Then we'll slap on multiples of 2 pi to get all the coterminal angles. What would the quadrant 2 angle be? Well, the quadrant 2 angle would need a reference angle there of the arc sine of 0.87. So how would I get to there? I can imagine rotating halfway around and then backing up that much, right? So I got to go halfway around to pi, except I'm backing up arc sine of 0.87. So the other answer, the quadrant 2 answer, would be pi minus arc sine of 0.87. So that would be the other angle here, pi minus that. Plus, of course, 2 pi k to capture all the coterminal angles to that one. Now this is going to tell me what 2x is, so to get what x is, I got to divide both sides by 2, which is the same as multiplying by a half. So I have to distribute a half to each of these terms. So I would get 1/2 arc sine 0.87 plus pi k, or x is pi over 2 minus 1/2 arc sine 0.87 plus pi k. And once again, this is good for integers k. Now, I expect I'm going to get 4 answers altogether because this sine wave is moving twice as fast as the regular sine wave, and the regular sine gives me 2 answers between 0 and 2 pi. So let's try to figure out what those would be. So in 0 to 2 pi, when k is 0, I'd get 1/2 arc sine 0.87. When k is 1, I'd have this plus pi. So I'd be taking half of this and then adding pi to it. So if I did that, that would land me somewhere in quadrant 3 somewhere. Okay. So I know that half of this is going to be, since this is between 0 and pi over 2, half of it would be between 0 and pi over 4. So if I add pi to it, that's going to give me something here in quadrant 3. So that's going to be less than 2 pi. If I add another pi to this, I'd have this positive number plus 2 pi, so I know I've overshot. Likewise, if I make k -1, I'd be taking this number, which is between 0 and pi over 4, and subtracting pi, which would give me a negative value. So I'm getting 2 solutions from this first family of solutions. Now I got to move to the second. When k equals 0 here, I get pi over 2 minus 1/2 arc sine 0.87. Once again, arc sine 0.87 is between 0 and pi over 2. So half of that's between 0 and pi over 4. So pi over 2 minus that would be a positive number. And it would be less than pi over 2. So it would be less than 2 pi. Now what if I add pi to this? If I add pi to this, I'd have pi plus pi over 2 minus 1/2 arc sine. So if I think about that, pi plus pi over 2 minus 1/2 arc sine, 0.87. That's 3 pi's over 2. So 3 pi over 2 minus a positive number would be certainly less than 2 pi, and it's going to be bigger than 0 because this is less than pi over 4. So that would be 3 pi's over 2 minus 1/2 arc sine 0.87. If I added another pi, I'd be at 5 pi over 2 minus something that's less than pi over 4, and that would be more than 2 pi. On the other hand, if I let k equal -1, I'd be subtracting pi off. So that would be a negative pi over 2 minus a positive number. That's going to be a negative, so that would be under 0. So these would be the 4 answers that live between 0 and 2 pi. Once again, those are the exact answers. They're not the nicest things, but they do the job. And you can, once again, approximate these or check your answer here on Desmos. So we'll do sine of 2x, and we'll do 0.87. You zoom in there. There's your 4 answers. So 1/2 arc sine 0.87. That should be the first one. There we go. Add pi. That should be this one here. Boom. So those are the 2 that are coming from the first family. The second family, pi minus that. That's the quadrant 2 answer. That should be the first one here. Excuse me, pi over 2 minus that. There. And then if I add pi to that, that's the 3 pi over 2, which is that one there. Okay? So if the reference angle is one that you know, like a pi over something that you know, that's great. If it's not, you can always use those inverse trig functions, the inverse circular functions we talked about in 10.4. All right, so that'll do it for example 2. We're faced with 3 sine cubed theta equals sine squared theta. And so the question is, how would we attack that? The goal would be, when you have this happening, is you want to get it down to like one of the equations we had in example 1, where you have trig function, trig function equal a number. And then you can go about and solve it like we did the basic equations earlier. So if we think about this sort of, what's actually happening here, remember that when you have sine cubed theta, that means sine of theta cubed, and this is sine of theta squared. And so this might make you think of polynomial equations, like if I had 3x squared, if I had 3x cubed equal x squared. All right, how would you solve something like this? 3 times something cubed equals that thing squared. You might want to divide both sides by x squared, all right? And that would work as long as your x squared isn't 0. In other words, you're not going to lose solutions. In this particular case, if we divided both sides by sine squared, we could be missing solutions because there are places where sine could be 0. So instead of dividing, typically we advocate subtracting and then factoring. And so that's the same algebra we're going to do here. This will enable us to help us isolate the sign, and then we'll be able to move forward with some more basic equations. So that's what we'll do. So from 3 sine cubed equals sine squared, I can subtract both sides. 3 sine cubed theta minus sine squared theta is 0. So I can factor that out. Sine squared theta (3 sine theta minus 1) is 0. And now that I factored things, I can set each factor equal to 0. So either sine squared theta is 0 or 3 sine theta minus 1 is 0. From sine squared theta equals 0, I can either take square roots or I could factor again. I'm going to have to get sine of theta is 0. From 3 sine theta minus 1 is 0, I can add 1 to both sides and divide by 3 and get sine theta is a third. So now I've got these two basic equations to solve. So for sine theta equals 0, that tells us we're working with quadrantal angles. In this case, we're working with where the y-coordinate is 0 on the unit circle. So that's going to be at 0 and then any pi multiple of 0. So this would give us theta equals 0 plus pi k, where k is any integer. But typically we'll just write this as pi k. Because when k is 0, I get 0. And so there we go. The other case is sine of theta is a third. Is that a legitimate sign value? Yeah, it's between minus 1 and 1. Is that a reference, or what quadrants would this be in? Well, I'd have solutions in quadrant 1 and quadrant 2. Is that a reference angle I know? It is not. That means I'll have to use the inverse sign, the arc sign. All right, so the reference angle I could take is the arc sine of a third. So the arc sine of the third would give me an acute angle here, which would serve as the reference angle for the quadrant 2. So one family of solutions would be arc sine of a third. plus any integer multiple of 2 pi. The other, well, I'd be coming over here, and I need the quadrant 2 angle, which with a reference angle of 1/3. So I can visualize that by going halfway around and then backing up. So I can think of halfway around as being pi, and then I'm backing up arc sine of 1/3, and then once again adding on multiples of 2 pi. So we've got 3 family of solutions. These encompass all the solutions. Which one lie between 0 and 2 pi? Well, from this first family, when k is 0, I get 0. So that's between 0 and 2 pi. When k is 1, I get pi. When k is 2, I get 2 pi. And we're technically not including 2 pi. So from the first family, we just get 0 and pi. From the second family, I get arc sine of 1/3. If I add 2 pi when k is 1, I'd be over 2 pi. If I let k be negative 1, I'd be less than 0. So we just get the one solution here, arc sine of 1/3. And last but not least, from the second family, I get pi minus arc sine of 1/3. Once again, if I added 2 pi to this, I'd be more than 2 pi. If I subtracted 2 pi, I'd be under 0. And so these represent our 4 solutions with lie between 0 and 2 pi. And once again, we can check this graphically. I think this will be the last one I check graphically for a while here. Anytime the arc functions are involved, people can get a little nervous. So we're graphing, we got 3 sine cubed theta equals sine squared theta. So I'm going to write 3 and then parentheses sine of x cubed, because I don't quite trust Desmos on some things. So that'll be my f of x, and this is a very groovy looking function. Look at that. That's pretty cool. And then I'll put g of x to be the right hand side of the equation, sine of x all squared, which is cool. I'm looking for where these two things cross. So it looks like there's 1, 2, 3, 4. Now that looks, see, a 2 pi, but we're not including the 2 pi there. All right, so we just have 1, 2, 3, 4 intersection points. This is funny, 0.33. That's funny. I mean, that's, I think, maybe round off error on Desmos. Oh no, wait, there's a 0, 0. There we go. Okay, so here's the 0 and pi, and then if I look at these decimals, those should match with our arc function. So arc sine of 1/3, and then pi minus arc sine of 1/3. Once again, make sure you're in radian mode here, folks, because when we solve these equations, we're looking for real numbers here. Those are radians. There we go. 0.33, blah, blah, 9, etc., and then 2.8. Boom. Okay. All right, so that'll do it for number 1. I've got secant squared theta equals tangent theta plus 3. So unlike the first example we had, we've got 2 different trig functions involved here. And it doesn't look like we can factor anything to get each trig function by itself. So when this happens, we try to use identities to convert everything in terms of one trig function. So we think back to our identities. One of the ones that hopefully we're comfortable with out of section 11.1 is that secant squared of theta, whoops, I lost connection here. Secant squared of theta secant squared of theta is 1 plus tangent squared of theta. That's one of those Pythagorean identities. And now I get everything in terms of tangents. So once again, let's think about the algebraic structure we've got here. I've got 1 plus something squared equals something plus 3. This is a quadratic equation. It's a quadratic equation in terms of tangent. So I can solve a quadratic equation like this by getting everything to one side, setting it to 0, and then either factoring or using the quadratic formula. So to do that, I'm going to keep the tangent squared theta on the left-hand side. I'll subtract off the tangent of theta. I'll subtract off 3. Subtracting 3 from 1 leaves me with 2. Which will be equivalent over here to x squared minus x minus 2 is 0. To solve this equation, I can factor. I can split x squared into x times x. I need factors of negative 2 that add up to negative 1, so x minus 2x plus 1, and then I'm on my way. So in the same way, I can factor this quadratic. I need factors that will multiply to give me tangent squared. So tangent and tangent. And then factors of negative 2 that add up to negative 1, negative 2, and 1. Now that I have things factored against 0, I set each factor equal to 0. So I get the tangent of theta plus 1 is 0, or I get the tangent of theta minus 2 is 0. So from the first equation, I subtract 1 from both sides. I get tangent theta negative 1. The second equation, I add 2 to both sides. I get tangent theta 2. So now we're going to solve these equations like we did equations that we had back in the previous sections. So first off, remember every real number is a good number for tangent. So tangent negative 1. What quadrants are we looking at? Once again, the period of tangent is pi, so once we get 1, we get everything by adding multiples of pi. So where's tangent negative? That's going to be when the x and the y coordinates have different SIGNs, plus or minus signs. That's going to be quadrant 2 and quadrant 4. Is this a tangent I know? Well, yeah. The reference angle there would have a tangent of 1, and that's a pi over 4. And I know a pi over 4. A pi over 4 that lives in quadrant 2 is 3 pi's over 4. So this one is going to be 3 pi's over 4 plus any multiple of pi. All right, let's look at the second equation here. Tangent of theta is 2. Going back to the unit circle. Those are going to be in quadrant 1 and then again in quadrant 3. Once again, these are pi apart, so I just need the quadrant 1 version. Do I know an angle whose tangent is 3? Well, I know an angle whose tangent is the square root of 3, but I don't know an angle whose, do I know an angle whose tangent is 2? And the answer is no. All right. So I got to use the inverse tangent, arctangent. So I can use the arctangent of 2. That's going to give me an angle here in quadrant 1. And then to capture all of those, I would tack on multiples of pi, and so on. So then I'd have to just list the ones that live in the interval 0 to 2 pi. So the first one here, 3 pi's over 4. If I add pi to that, I'm adding 4 pi's over 4. That's 7 pi's over 4. Those are two angles that we know from the unit circle. If I add pi again, I'm over 2 pi. If I subtract pi from the 3 pi over 4, I'm less than 0. So those are the two answers I get here. From the second family, I'm going to pick up the arctangent of 2. That's between 0 and pi over 2. If I add pi to that, that's going to put me there in quadrant 3. Arctangent of 2 plus pi. If I add another pi, I'm going to be over 2 pi. If I subtract pi from arctangent of 2, since arctangent of 2 here is in quadrant 1, I'd be less than 0. So those are my 4 answers. So theta is 3 pi's over 4, 7 pi's over 4, arctangent of 2, and then arctangent of 2 plus pi. And once again, you can verify those on Desmos. So we find all the solutions, and then we pick out the ones that fit where we want them to be. Okay, number 3, we're sort of in the same boat as we were with number 2. Well, actually, no, it's a slightly different boat. In number 3, we have the same trig function, namely cosine, but we have different angles. We have 2t and t. So once again, we're going to have to use an identity to help us get everything in terms of the same trig function with the same angle. Now, as fate would have it, cosine of 2t, we have 3 versions of that identity. I can replace that with cosine squared t minus sine squared t. I can replace that with 1 minus 2 sine squared of t, or 2 cosine squared t minus 1. Given that the right-hand side of the equation has just cosine t in it, that's going to be the selection we choose. Now, once again, if I think about this algebraically, I've got 2 times something squared minus 1 is 3 times that thing minus 2. This is a quadratic equation. I would subtract 3x over, add 2 over, and then I would attempt to factor. If factoring didn't work, I'd have to hit it with quadratic formula. So that's the same strategy I'm going to use here. So I'm going to have 2 cosine squared t minus 3 cosine t plus 1 equals 0. And now I'm going to try to factor this. So I need factors of 2 cosine squared t that are going to multiply to give me 2 cosine squared t. So one of the factors will have a 2 cosine in it if it's going to factor nicely. The other will have a factor of cosine t. And now I need factors of 1 that are going to somehow combine with these to get me to a negative 3. Well, the only way that's going to happen, the only nice factors of negative 1 that are going to give negatives are negative 1 and negative 1. So let's just check. 2 cosine t times 2 cosine t, that's my 2 cosine squared t. If I take a 2 cosine t times a negative 1, and then a negative 1 times a cosine t, sure enough I get to negative 3 cosine t. Negative 1 times negative 1, that's positive 1. So now that I have factored 2 things to 0, I've got 2 things multiplied together to give me 0. That means one or the other of those things has to be 0. So either 2 cosine t minus 1 is 0, or cosine t minus 1 itself is 0. From the first equation, I get cosine of t would have to be a half. From the second one, I get the cosine of t is 1. So now I have 2 of these equations to go solve. So let's take a look at cosine of t is a half. First off, is that a legitimate number for the cosine? Sure, it's between minus 1 and 1. Secondly, what quadrants are we looking at? Cosine is positive in quadrant 1 and quadrant 4. Do I recognize the reference angle for this? Yeah. The reference angle here is pi over 3, and that's going to be the first quadrant solution. So t is, pi over 3 plus any multiple of 2 pi or, I don't know why my tablet's acting up here, or t is what? That's your 5 pi's over 3 plus any multiple of 2 pi. any integer multiple of 2 pi, I should say. Those are the answers there. Now what about cosine of t is 1? That was my other solution here. Cosine of t is 1. Well, that's a quadrantal angle, right? Cosine of t is 1. That's where the x coordinate on the unit circle is 1. That's just this point here, which is just going to be t equals 0. Plus, of course, any multiple of 2 pi. So that's just 2 pi k, where k is plus or 0 plus or minus 1 plus or minus 2. So in the interval 0 to 2 pi, what are my answers? Pi over 3, 5 pi over 3, and then 0. Adding or subtracting multiples of 2 pi to any of these values is going to result in numbers that are either bigger than 2 pi, equal to 2 pi, or less than 0. Last example here, we're looking at cosine of 3t equals 2 minus cosine t. So all we did is just change the frequency here from 2 to 3. So how does that upset the apple cart? Well, we don't have a triple angle formula for cosine memorized, but we did actually derive one. Cosine of 3t turns out to be 4 cosine cubed t minus 3 cosine t. Right? Something we had from before. We can check this. We'll just be consistent here. We'll check it on 0 to 2 pi. So there we go. So it's, it's legit. Whoops, didn't mean to do that. Okay. So I could write this as 4 cosine cubed t minus 3 cosine t is 2 minus cosine t. And thinking algebraically, I've got a polynomial. 4x cubed minus 3x is 2 minus x. So I can solve this like we solved polynomials back in college algebra, namely add x to both sides and subtract 2 to both sides to get to 4x cubed minus 2x minus 2 is 0. And then we go in and do what we have to do here. Okay? So let's talk about this. That's what we'd have to solve. All right. So when you have polynomials at a degree more than 2, right? So things that are beyond quadratics. Typically we graph the polynomial, we look to see what roots look good, use synthetic division and all that other good stuff. All right, so let's take sort of a trip down memory lane here with the college algebra. Let's just look at this polynomial and we'll try to solve that using what we learned in college algebra. So we'll fire this up, we'll turn this off, and we'll put in our polynomial. P of x is 4x cubed minus 2x minus 2. And, well, look. We're setting it equal to 0. That means we're looking for the zeros of the function. We're looking for the x-intercepts. 1 looks good. Okay, so remember this? So 1 looks good. Looks like it's got multiplicity 1. And to prove that that's the only one we have, we would do that synthetic division. So x equals 1 looks good. Whoops. So we can check that by doing our synthetic division. So we're going to divide 1 in, which is really, we're dividing the quantity x minus 1 in. And then I write down my coefficients. I've got 4x cubes, no x squareds, minus 2x's minus 2. Bring down the 4, multiply and add, multiply and add, multiply multiply and add, and sure enough, we've got a winner. 442 corresponds to 4x squared plus 4x plus 2 equals 0. Now, based on the graph of the polynomial, it didn't appear as if we had any other solutions. So let's just check here with my b squared minus 4ac discriminant. That would be b squared would be 16 minus 4 times 4 is 16 times 2 is 32. That's going to be less than 0. So that means that this quadratic doesn't give you any real solutions, which means the only solution we get is x equals 1. Okay? So that's the algebra happening back here. So what does that mean for us? Back in trigonometry land, right? So the only solution here, x equals 1, means the only solution here is the cosine of t is 1. And we know cosine of t is 1. Between 0 and 2 pi, the only solution to that is when t equals 0. Right? So on the unit circle we're looking at here. So this is one we had before. We only pick up t equals 0. So this is a whole lot of work for nothing. Right? Just a pun, because the only solution there is t equals 0. Let's fire up Desmos and now check the trig version of this to make sure we're not missing anything. Messed up here. So this would be cosine of 3x, and then the right hand side was 2 minus cosine x. And sure enough, if I look, that's a cool picture, huh? That's why I love Desmos. That's a cool picture. Looks like almost like a Pac-Man ghost. There's the only answer. Now it's picking up the 2 pi, but remember we're looking strictly between 0 and 2 pi. Right, so you can, since this is a bit of a scary thing, we had to go back to college algebra, right? This is a bit of a scary problem. It makes sense that would look like one of those Pac-Man ghosts. Okay, so that'll do it for that example.